Hello again, assembler class. This next talk is going to be about negative numbers. I agree, you probably did negative numbers many years ago, and you think you got it knocked. And you do, but negative numbers in binary are going to be a trifle different. So let's make a negative number. We'll start by making a minus 13. And to make a minus 13, I want to start with a plus 13. And for today's video here, we're just going to be using 6-bit numbers, which is like not natural in the sense that there aren't any computers that have 6-bit numbers. Okay, that's fine. The principle is the same. You can extend it to however many bits you need. So I'm going to start with 13. We wanted to make minus 13. So 13 in binary would be 0, 0, 1, 1, 0, 1. So that's plus 13. Okay. All right. Now, here is, I guess this is sort of near the top of the screen, so we'll move it down a little bit because I need to do a little carrying. Okay. Still sort of near the top of the screen there. Okay. Okay. So that's 13 in binary. And what I want to do is I want to find a number which, if I add it to this thing, I'll get 0. That's how I'm going to define minus 13. Now, the problem we have is that we don't really have a way of writing negative numbers in binary. All we have is strings of bits. And we know this bit represents the 1s, the 2s, the 4s, the 8s, 16s, and 32s, right? And we only have 0 and 1, so we don't really have like a minus sign or anything like that. So, lacking a way to represent that, I'm going to try to figure out something which I can add to 13 which will get me 0. And in order to do that, I'm going to have to cheat. Okay, we'll cheat. All right, so let's start by flipping all the bits. So it's called complementing the bits. If you complement a 0, you get a 1. You complement a 1, you get a 0. So flip all the bits. That'll be 0, 1, 0, 0, 1, 1, right? If I add this, what do I get? Well, that's easy. I had a 1 here. It became a 0. 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 1 is 1. 0 plus 1 is 1. Excuse me, I wrote a 0 there by mistake. Okay. This is like trivially easy. If I flip the bits and then add them up, I'm going to get that, right? No problem. Now comes the part where I cheat. I'm going to add 1. So now we're adding, just like you did in grade school, but we're doing it in binary. 1 plus 1 is 2, right? 2, 1, 0 in binary. So that's a 0 with 1 to carry, right? So 1 plus 1 is 0 and 1 to carry. 1 plus 1 plus 0 is 0 and 1 to carry. 1 plus 1 is 2 plus 0 is 0 and 1 to carry. 0 and 1 to carry. 1 plus 1 is 0 and 1 to carry. 1 plus 1 plus 0 is 0 and 1 to carry. So normally what you would do is you'd put like that. This is our answer. However, However, I said at the beginning we are using 6-bit binary numbers. And this over here is kind of off the end of the 6-bit binary number. It's like if we had a box which was 6 bits big, we're trying to cram a 7th bit into it. So we just say this guy goes bye-bye. And that leaves us with 0. I told you I wasn't going to play fair. All right, why is this actually playing fair? This is actually playing fair because if you think about the electronics has bytes or 16-bit, words, or 32-bit words, or some number of bits in a register or a memory location. Okay, so inside the computer, it has some hardware made out of little flip-flops or something similar, some bi-state devices, that each one represents a bit. So 1 byte in memory has 8 little bits in it and no more. So when I say I'm at 6 bits, representing in hardware, there are 6 flip-flops here in a circuit, and then this part over here, there is no circuitry there. So we really did lose that bit. And we really didn't have any place to put it. It's gone. We had 6 physical bits in the machine. There they are. This guy, well, what happens? Well, I say it fell off the end. It went down into a bucket. At the end of the day, we collect all these bits which overflowed off the end. We melt them down and we reuse them. Okay? Something like that. Anyway, it's gone. Wherever it went, it's gone. All right? So this says that if I took a number, I flipped the bits, and then I added 1, that could get me to the negative. So let's try it. Here we had 13. We'll flip the bits. We'll add 1 to this. Before we flipped the bits, added it in, added 1 more, right? Let's do the add 1 now. Okay? So instead of plus flip plus 1. This is what we did a moment ago. We said to 13, we added in the flipped, then we added a 1, right? We're going to parenthesize this a little differently. We're going to calculate the flipped plus 1, and we're going to add 13 plus the flipped plus 1. All right, we're just parenthesizing this differently. I claim if we get 0 out, then this will be minus 13. Okay. I claim that flipped plus 1 should be equal to minus 13. All right. Think you can do it? Let's do it. So here's the flipped. Add 1. This is now the flipped plus 1. One plus 1 is 0, 1 to carry. 1 plus 0 plus 1 is, that's 2 is 0 and 1 to carry. 1 plus 1 is 0 is 0, 1 to carry. 0, 1 to carry. 0, 1 to carry. 0, and then we get our 1 which came off the carry over here, and we have our answer. 13 plus a negative 13 is equal to 0. Okay? Does this work the other way? If I started with a negative 13, would I get 13 out? Here was my negative 13. My negative 13, if you recall, was 1, 1, 0, 0. 1, 1. Nope, that was negative 13. All right. If I flip it, I'll get 0, 0, 1, 1, 0, 0, and then I'll add 1, 0, 0, 1, 1, 0, 1, and that's 13. Minus 13 plus 13. So I started with minus 13. I flipped it. I added 1. I got 13 out. So this flipping and adding one thing is a reversible operation. That's good, right? Okay. Shall we just try one more real quick? Okay. Let's try, what do you want to try? So how about 29, okay? 29 is going to be 0, right? And then we have a what? We have a 16, right? And then, so that's going to be 16 plus 13. So why don't we try 27, okay? 16 plus 7, right? Or for 27, it's plus 9. All right, that's equal to 27. So that's 16 plus 8 is 24. What am I doing right? Oh, it says 16 plus 25, 27. All right, that's 27. I finally got it. Sorry, guys. Okay. That's 27. Let's try flipping it. Flip is going to make 1, 0, 0, 1, 0, 0. Add 1, 1, 0, 0, 1, 0, 1. That should be minus 27. So I flipped the bits from 27. I added 1. 1 with 1 is 0, 1 to carry, 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 0, 1 to carry. And we've got our minus 27. Happiness? Okay. The thing to remember is that in some ways, the way you look at a bunch of bits in computer memory is kind of arbitrary. We could look at this number as a minus 27. Or if I say, I don't care about negative numbers. I have 6 bits. I want to have 6 bits of pure binary. Forget the negatives, right? If I did that, what do I have? Okay, 42. Well, 43, sorry. Some number like that. It was 32 plus 37, I'm sorry, 37. And 37. So this could be a positive 37. 16 plus 4 plus 1. No, 32 plus 4 plus 1. It could be a positive 37. It's a minus 27 if I think of these as 32-bit signed, no, excuse me, 6-bit signed numbers. Or it's a plus 37 if I think of these as 16-bit numbers that don't have negatives, unsigned numbers. It's the same bit pattern. 6 bits, ones and zeros. If I wake up in the morning and say, I'm dealing with negative numbers, it's a minus 27. If I wake up in the morning and I say, I don't care about negative numbers today, it's a plus 37. And this turns out to be true in assembler also. Okay. Depending upon what I'm doing, I can think of it as positive or think of it as negative. There are few assembler instructions which will just be dependent upon using unsigned numbers or signed numbers. The actual bit patterns in memory are going to be like this. All right? So that's another like really crucial assembler computer lesson. That the bit pattern in memory could mean different things depending upon how you are thinking about that bit pattern and how you're computing with it. Okay? So that's negative numbers, which had more lessons in it than you probably thought. Metaphysical lessons about it. What does it really mean? Up to you.